We have seen the linearity property of expectation. So if we have a linear function of single random variable, the expectation behaves in linear fashion. So if you observe carefully here, this is a linear function of random variable x. So random variable x is getting multiplied by some constant a, and we have added some constant b. If you try to find the expectation of it, the same thing will happen to the expectation also. The expectation of this random variable x will also get multiplied by a, and the same term b will also get added. We have already seen this. If you haven't, then I would recommend to go through my previous lectures. But now if we have multiple random variable, we have a additional property. First of all, let me write down this additional property. So let's say we have this random variable x and y. So if we try to find the expectation of this random variable, sum of this random variable, that is expected value of this x plus y, that would be the sum of individual expectation. So the expected value of sum of two random variable is equal to the sum of their individual expectation. How? Let's go through this derivation. So what we can do, we can simply, let's assume that this sum is a function. So g is a function that is the sum of these two random variable, and now we can use the expected value rule. So basically the expected value rule is the by using expected value rule, we can find the expectation of a function that we have already gone through in one of our videos. So I strongly recommend that watch all of the videos so that you would be easily able to relate each and every terms and the concept, right? So if we use the expected value rule, we can simply find the expectation of this function, that is the expectation of this function g xy, right? So here the function is x plus y, the function is gx, that is x plus y, right? And it will be weighted by the joint probability, because to get this sum you need to have x as well as at the same time what will be the value of y, then only you will be able to get the sum, right? So that will be weighted by the joint probabilities, and this we sum over all the possible values of x and y. So this is how we find the expectation of any function, right? That is what we have learned in expected value rule. Next, what we can do, we can simply separate the x and y terms. So let me proceed further. So that will be, so let's the x term, x times the joint probability, and plus y times this joint probability. Now you see this summation, the inner summation here, this summation depends on this value y, right? So we can think this as a constant because this is x, so we can simply put outside this summation, so that will be equal to summation over x. So we can simply put the x outside this summation. Now let's look at this term. What is this? So what we are doing, for a specific value of y, we are summing over, sorry, for a specific value of x, we are summing over y. So this is nothing but the marginal PMF of random variable x. So we can simply write this as a marginal PMF of this random variable x, right? And now look at this term. What is this? X times the probability of this random variable x, and we are summing this term for all the possible values of x. So this is nothing but the expected value of random variable x. Similarly, we can do for this term also, right? So here we can write like this. Right, and this summation is on over x, so we can simply put this y outside of this summation. So let me do that. So if you look at this term, this summation, so you are summing over x. So for a specific value of y, you are summing over x with for this probability, right? So this is nothing but the this is nothing but the marginal PMF of this random variable y. So that will be y times the marginal PMF of this random variable y. And again, if you look at this, y times the probability of this random variable y, and we are summing over this term for all possible value of y. So this is nothing but the expected value of random variable y. So we can write like this. So random variable of this function is nothing but the expected value of this function, that is g, is nothing but the expectation of the sum of this random variable, that is x plus y, is equals to the individual expectation. Okay, so we proved the linearity property for the case of sum of two random variable, but we can proceed in similar way, or maybe we can use the induction and can easily establish by following the same kind of argument that we have linearity property when we have finite number of random variable. The expected value of sum is the sum of the individual expectation. We can take a simple example. Let's say if we have to find the expected value of this, where x is a random variable, 3 times this random variable y minus z, that would be simply equal to the individual expectations, that will be this plus expectation of this random variable 3 y minus expectation of this random variable z. We can simply put out using the linearity this constant outside the expectation. Similarly for this also, and this is what we will get. Now we will use this linearity property to find the mean of binomial random variable, or the expected value of this binomial random variable. So binomial random variable, so we deal with a kind of experiment where we do n independent trials, and we define a random variable that from n independent trials the number of success. Or if we have to talk in terms of the coin tossing model, if we are doing n independent tosses, then if we define success as getting the number of hits, then this random variable will defined as number of hits, how many number of hits will be there in an independent trial. So if you are not familiar with this binomial random variable, I would recommend to watch my previous videos. Right now we want to find the expected value of this random variable x. So as usual, we can use the expected value, how we find the expected value of a random variable. So if you know the PMF of this binomial random variable, so we might get the success out of n trial, we might get the success k times, right? And the getting the success probability of getting the success is small p. So if you are already familiar with this binomial random variable, you will not have the difficulty. And maybe out of n trials, we get the k success, and n minus k we will have no success, right? And how many such sequence will be there? That will be n choose k sequence, right? And this is the PMF of this binomial random variable, and we are trying to find the expectation of this binomial random variable. So we will multiply here k, and this summation will go from k is equals to 0 to n, right? So this is the expectation of this binomial random variable, right? But if you look at this sum, it would be little bit complex to find this sum. You will be able to find this, but it will be somehow little bit difficult. So instead what we will do, we will use this property to find the expectation of this binomial random variables. We can easily do that. Let me do that. How we can do that? So we are going to consider a random variable. Let's suppose we have a random variable. Let's define this random variable as xi is equals to 1 when the ith trial is success. When ith trial is success, and this random variable xi will be 0 when otherwise. We can simply write otherwise, right? And what is this random variable x? Is this random variable x is the number of successes in an independent trial. So here the trick is, you can simply write this random variable x as a sum of these individual random variables, right? So how many success you will get, that depends on how many ones you have got, right? So either you will get the 1 or you will get the 0, right? So if you add all these count, whatever you have got in ith trial, then this will give you the total number of successes in n trial, right? So what we have done, so this is the random variable and this is also random variable, right? So we have simply split this complex random variable into some simple random variable, right? And now we can use the linearity property to find the expectation of this random variable x. So that will be simply the expectation of this random variable x1, the expectation of this random variable x2, plus this expectation of this random variable xn. And if you look at these random variables, so these random variables, either this random variable, so not only this random variable, so these are the same random variable, either they can take the value 1 or 0, right? So these are nothing but the Bernoulli random variable, and you know the expectation of this Bernoulli random variable, that is simply the small probability p, right? And each one of these are the Bernoulli random variable. They can either take the 0 or 1, right? So each will have the expectation small p, and this summation will be n times p. So the expected value or the expectation of Bernoulli random variable would be n times p, where n is the number of trials and p is the probability of getting the success. Alright, otherwise if you would have gone through this expression, it would be mathematically little bit complex. What we have done, we have simply break down the problem into simpler random variable, and we have used the linearity property to find the expectation of this binomial random variable. Okay, that is all in this